Students often wonder where the idea for momentum comes from. Well, it comes from Newton's second law. This is Newton's second law. The net force acting on an object is equal to that object's mass times its acceleration. This is a vector equation. So the force and the acceleration are the only vectors here, and they have to point in the same direction. When we multiply acceleration times a scalar, it doesn't change the direction. So net force and acceleration always point in the same direction. But we know the acceleration is equal to the rate of change of velocity with respect to time. So we can substitute this back in. And if the mass is constant, we can bring it in and write it this way. And now we can ask, what happens if the net force is 0? Well, if the net force is 0, we have a time rate of change of mv equals 0. Or another way of writing that is m times v is a constant. It does not change in time. So there's something special about this quantity m times v. If the net force on our system is 0, this quantity has to be the same. It has to be conserved. And that's where the idea came from. Let's call it its own special name. Let's call it momentum. So mv is its own special quantity. We call it momentum. And we use a lowercase p for that. Again, this is a vector equation. Momentum gets its direction from the velocity of the object. And as you can see here, a big, massive object moving fairly slow can still have a lot of momentum. And a small object has to move very fast to have a high amount of momentum. But it's a combination of mass and velocity. Impulse tells us how momentum changes. Some books use capital I for impulse, some books use capital J, but the impulse is a vector quantity. It gets its direction from the net force. The impulse points in the same direction as the net force acting on our object. And it's equal to the force times some time interval. If the force is not constant over that time interval, we have to integrate to find the impulse. If the force is constant, we can just multiply it by the time interval. Let's work through a few examples. Let's start with the simple one. Find the momentum of our object. Momentum is just mass times velocity. So we get 24. Did you remember your units? Kilogram meters per second. And your answer would not be complete without a direction because momentum is a vector quantity. So we need to include the direction to the right. Now let's do this one. Find the momentum of our object. This time it's 14 kilogram meters per second to the left. It's not negative 14 because we have not defined a positive direction. If you put on your paper somewhere a coordinate system, then you could write this as negative 14 kilogram meters per second in the x hat or I hat direction. You can use unit vector notation. But if you don't do this step, you better not put a negative sign down. It's meaningless without a definition of what your positive direction is. This time we're going to find the change in momentum of our object. The first example here, we have a 2 kilogram object. It starts out moving at 3 meters per second to the right. Something happens to it and it ends up moving at 5 meters per second to the right. We want to know the change in momentum. And I'd like you to do it two ways. First, use graphical vector addition. Remember how to do graphical vector addition? You add vectors tip to tail. use graphical vector addition to find your change in momentum. And then just use your equation. So delta P, the change in momentum, is final minus initial. The final momentum is 10. So I'll use green here for the final momentum. And I'm going to subtract, I'm going to add the opposite of P initial. The initial momentum is 6 kilograms meters per second, but I'm going to add the opposite of that. It points to the right, but that negative sign in front of a vector rotates it by 180 degrees. So I'll use gray for this. So I'm going to add the opposite of that. So I come out to the tip of this vector, and 1, 2, 3, 6 units. That is the opposite of P initial. And when I add those two together, what do I get? I get this vector right here. 4 kilogram meters per second to the right. Remember, delta P is also a vector quantity. It needs units for sure, and it needs a direction associated with it. That's doing the graphical approach, but we could have done it just with an equation. What do we have to do first thing before we use an equation? We have to define our positive direction. So let's call the right our positive direction, and then we know that delta P is going to be P final minus P initial. P final is 10 kilogram meters per second in the positive direction. I'll just put a little plus sign there so we know it's positive. And we are going to subtract P initial, which is also in the positive direction, and it's 6. So we end up with a positive 4 kilogram meters per second, and positive means to the right. This time, our 2 kilogram object starts out moving 3 meters per second to the right, and it ends up, after something happens to it, some force acts on it, it ends up moving 3 meters per second to the left. And you're going to find the change in momentum using our two techniques. First, using our graphical technique, we are going to first draw P final. P final is 6 kilogram meters per second to the left. I look at the velocity and I multiply it by the mass. And I'm subtracting P initial. P initial is 6 to the right, but because I'm subtracting, I'm adding the opposite of that. And I come out to the tip of this vector and I add the opposite of P initial. And when I add them together, I get this vector right here. 12 kilogram meters per second to the left. This time, we're going to find the impulse. Well, the impulse is the same thing as change in momentum. We can define our coordinate system, and then we know that the impulse is equal to the change in momentum. It's the final momentum, and that's going to be 14 kilogram meters per second in the negative direction, because our particle is moving to the left, and we've defined the right as our positive direction. And then we are going to subtract 6 kilogram meters per second in the x direction, and we're going to end up with negative 20 in the x direction, or if you prefer, I hat. So units and direction always with your answer.